Hello there, and welcome to the Sleepy Library. I am so glad you found your way here tonight. Perhaps you have had a long day, or perhaps you are simply the kind of person who prefers falling asleep to quiet thoughts about the cosmos, rather than counting sheep. Either way, tonight is for you. You have nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened its hold. Tonight, we are traveling through the realm of moons, not just our own pale companion in the night sky, but the hundreds of natural satellites that orbit planets throughout our solar system. These worlds are far more than simple rocks circling larger bodies. They are ice-covered oceans hiding beneath frozen shells, volcanic landscapes more active than anywhere on Earth, seas of liquid methane under alien skies, and ancient surfaces that remember the earliest days of our cosmic neighborhood. They are companions, guardians, and mysteries all at once. We will wander gently from moon to moon, learning their secrets and marveling at their quiet beauty. Some hold oceans twice the size of all Earth's waters combined. Others erupt with fountains of ice that reach thousands of miles into space. A few have atmospheres thicker than our own, while many have surfaces so reflective they shine like polished mirrors. Each one tells a story about gravity, time, and the endless creativity of nature. If these calm explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, settle in, let the night fold around you, and let us begin. Our own moon is the fifth largest moon in the entire solar system. When you look up at night and see its familiar face, you are looking at a world roughly 1/4 the size of Earth. It stretches about 3,400 kilometers across, making it larger than Pluto and many other distant worlds. Among all the moons that orbit planets in our solar system, only 4 are bigger: Ganymede and Callisto at Jupiter, Titan at Saturn, and Io at Jupiter. Our moon stands as a giant among natural satellites, especially for a planet as small as Earth. Its size relative to Earth is unusual, giving our planet an almost binary quality, as if two worlds orbit their common center of gravity together through space. The moon formed from a colossal collision billions of years ago. Around 4.5 billion years ago, when Earth was still a young and molten world, another planet, roughly the size of Mars, crashed into it. The impact was unimaginable, vaporizing rock, melting the surface, and throwing massive amounts of debris into orbit around Earth. Over time, this cloud of molten material gradually clumped together under its own gravity, cooling and solidifying into the moon we see today. This theory, known as the giant impact hypothesis, explains why the moon's composition is so similar to Earth's outer layers, and why it has almost no iron core compared to Earth. The moon is, in essence, a piece of our planet, torn away and shaped by one of the most violent events in our world's history. That ancient scar became a companion that has watched over Earth ever since. The moon moves away from Earth at about 3.8 centimeters per year. This gradual separation has been happening for billions of years, and it is caused by the same tidal forces that create ocean tides on Earth. As the moon pulls on Earth's oceans, creating bulges of water, Earth's rotation drags those bulges slightly ahead of the moon. This creates a gravitational tug that slowly accelerates the moon in its orbit, pushing it farther away. Millions of years ago, the moon was much closer to Earth. Days were shorter, and the moon appeared much larger in the sky. In the distant future, the moon will continue to recede until it reaches a stable distance. For now, it inches away quietly, a slow cosmic waltz that has been unfolding since the moon's formation. The moon has no atmosphere to speak of. When astronauts walked on the lunar surface during the Apollo missions, they experienced a world utterly silent and exposed. Without an atmosphere, there is no wind, no weather, no sound. Footprints left by astronauts in the fine lunar dust remain perfectly preserved because there is nothing to erode them. The lack of atmosphere also means the moon's surface experiences extreme temperature swings. In direct sunlight, temperatures can soar to over 120 degrees Celsius, while in shadow, they plunge to -170 degrees Celsius. This harsh environment makes the moon's surface one of the most extreme places in our solar system. Yet it remains hauntingly beautiful in its stillness and simplicity. Earth's moon is covered with impact craters from billions of years of bombardment. When you look at the moon through a telescope, or even with your naked eye, the dark patches and bright highlands tell a story of cosmic violence. Early in the solar system's history, countless asteroids and comets crashed into the moon, carving out craters of all sizes. Some are small, just a few meters across, while others, like the South Pole Aitken Basin, span over 2,000 kilometers and represent one of the largest impact structures in the entire solar system. Because the moon has no atmosphere or tectonic activity to erase these scars, they remain as a permanent record of the chaotic early days when worlds were still forming and collisions were common. The moon is, in a way, a cosmic museum, preserving the memory of impacts that would have long since vanished on Earth. The moon's gravity is only about 1/6 that of Earth's. If you could stand on the lunar surface, you would weigh roughly 6 times less than you do on Earth. This low gravity is why astronauts appeared to bounce and move in slow, graceful arcs during their moonwalks. It also explains why the moon cannot hold onto an atmosphere. Any gases that might have once existed simply escaped into space. The moon's gentle pull shapes everything about its nature, from the way dust settles on its surface to the slow, measured way objects fall. It is a world where movement feels dreamlike, where every step would carry you farther, and every jump would lift you higher than you could imagine on Earth. There are more than 890 confirmed moons in our solar system. As of early 2025, astronomers have identified at least 891 natural satellites orbiting planets, dwarf planets, and even some asteroids. These moons come in every imaginable variety. Some are massive worlds with thick atmospheres and underground oceans. Others are tiny, irregular chunks of rock, barely a kilometer across. Saturn alone has at least 274 confirmed moons, making it the planet with the most known satellites. Jupiter follows with 97 known moons. Even distant dwarf planets like Pluto and Eris have their own small families of moons. The solar system is not just a collection of planets orbiting the Sun. It is a vast community of worlds within worlds, each moon adding its own unique character to the cosmic neighborhood. Most moons orbit in the same direction as their planet's rotation. These are called regular moons, and they typically formed from the same disk of gas and dust that created their parent planet. They orbit close to the planet's equatorial plane, following neat, nearly circular paths that remain stable for billions of years. But not all moons follow these rules. Irregular moons orbit at strange angles, sometimes even backward compared to their planet's spin. These moons were likely captured by the planet's gravity after forming elsewhere, perhaps as asteroids or fragments from other parts of the solar system. Their tilted and elliptical orbits reveal their outsider status, marking them as travelers who found a new home far from their birthplace. Mercury and Venus are the only planets in our solar system without moons. Mercury, being so close to the Sun, likely had any potential moons stripped away by the Sun's powerful gravity. Venus, despite being Earth's twin in size, also has no natural satellites. The reasons for Venus's lack of moons remain uncertain, though some scientists speculate that any moon it might have had could have been destabilized by a combination of the Sun's gravity and Venus's slow, backward rotation. Among the 8 planets, Mercury and Venus stand alone, orbiting the Sun in solitude without the companionship of a natural satellite. They are the exceptions in a solar system where moons are otherwise abundant. Jupiter's moon, Ganymede, is the largest moon in the entire solar system. With a diameter of about 5,268 kilometers, Ganymede is not only larger than our own moon, it is even bigger than the planet Mercury. Ganymede orbited the Sun instead of Jupiter. It would easily qualify as a planet in its own right. This enormous moon has its own magnetic field, the only moon in the solar system to possess one, generated by a liquid iron core deep within. Ganymede's surface is a patchwork of ancient dark terrain scarred by countless craters and younger, brighter regions marked by grooves and ridges. Beneath its icy crust, scientists believe there is a vast ocean of liquid water, potentially containing more water than all of Earth's oceans combined. Ganymede is not just a moon, it is a world unto itself, complex and fascinating in ways that continue to surprise researchers. Titan is the only moon in our solar system with a thick atmosphere. Orbiting Saturn at a distance of about 1,200,000 kilometers, Titan is the second largest moon in the solar system, and the only one where atmospheric pressure at the surface is greater than Earth's. In fact, standing on Titan's surface would feel like being about 15 meters underwater on Earth. The atmosphere is composed mostly of nitrogen, just like Earth's, but with a significant amount of methane as well. This thick blanket of gases creates a kind of smog that completely obscures the surface from view in visible light. The atmosphere is so dense that it extends 10 times higher than Earth's atmosphere, reaching nearly 600 kilometers into space. Titan is unique among moons, a place where weather, wind, and seasons all play out beneath an alien sky. Titan has lakes and seas of liquid methane and ethane on its surface. This makes it the only place besides Earth where stable bodies of liquid exist on the surface. However, instead of water, Titan's lakes are filled with hydrocarbons, the same chemicals that on Earth we use as natural gas. The largest of these liquid bodies, Kraken Mare, is bigger than the Caspian Sea on Earth. Near Titan's North Pole, dozens of smaller lakes dot the landscape, some connected by channels that resemble rivers. The liquid cycles through Titan's atmosphere much like water does on Earth. Methane evaporates from the surface, forms clouds, falls as rain, and flows back into the lakes. On Titan, it can rain methane. The raindrops would be twice as large as those on Earth and would fall much more slowly through the thick atmosphere, creating a surreal, almost hypnotic precipitation. The temperature on Titan's surface is about -179 degrees Celsius. This extreme cold is necessary for methane and ethane to exist as liquids, just as water needs Earth's moderate temperatures to remain in liquid form. On Titan, water ice is as hard as rock, forming the bedrock and mountains of the landscape. Any volcanic activity that might exist would erupt not with molten rock, but with liquid water mixed with ammonia, a phenomenon scientists call cryovolcanism. Despite the frigid temperatures, Titan's thick atmosphere acts as an insulating blanket, even more extreme temperature swings. The cold is constant and pervasive, yet within this frozen world, an active and dynamic environment thrives, with weather patterns, erosion, and geological processes that mirror Earth's in strange and wonderful ways. Beneath Titan's icy crust lies a subsurface ocean of liquid water. This ocean, likely mixed with salts and ammonia, is estimated to be about 50 to 80 kilometers below the surface. Evidence for this ocean comes from measurements of Titan's gravitational field and the way radio signals behave as they pass through the Moon's interior. The ocean is kept liquid by heat generated from tidal forces as Titan orbits Saturn and from the decay of radioactive elements in the Moon's rocky core. This hidden ocean adds Titan to the growing list of ocean worlds in our solar system, places where liquid water exists beneath an icy shell, and where the conditions for life, as we understand it, might possibly exist. Titan's combination of a surface rich in organic chemistry and a subsurface ocean makes it one of the most intriguing places to search for life beyond Earth. Io is the most volcanically active body in the entire solar system. Orbiting Jupiter at a distance of about 422,000 kilometers, Io is caught in a gravitational tug-of-war between Jupiter and its neighboring moons, Europa and Ganymede. This gravitational interaction keeps Io's orbit slightly elliptical, causing Jupiter's immense gravity to squeeze and stretch the Moon with each orbit. The friction generated by this constant flexing heats Io's interior to extreme temperatures, creating a molten subsurface layer and driving hundreds of active volcanoes across its surface. Some of these volcanic plumes erupt with such force that they shoot material 300 kilometers into space, far above the Moon's surface. Lava flows on Io can stretch for hundreds of kilometers, and the surface is constantly being renewed by fresh volcanic deposits. In a way, Io never grows old. Its surface is perpetually young, reshaped and reborn by relentless volcanism. The tidal forces on Io are about 20,000 times stronger than those the Moon exerts on Earth. As Io orbits Jupiter, the giant planet's gravity pulls more strongly on the side of Io facing it than on the far side, creating a tidal bulge. Because Io's orbit is elliptical, the strength of this pull varies, causing the Moon's shape to change by as much as 100 meters between its closest and farthest points from Jupiter. This constant squeezing and relaxing generates tremendous heat through friction, a process known as tidal heating. The amount of energy produced by tidal heating on Io is about 200 times greater than the energy produced by radioactive decay inside Earth. This makes Io a furnace among moons, driven not by its own internal processes, but by the relentless grip of Jupiter's gravity. Io's surface is painted in shades of yellow, orange, red, white. These vivid colors are created by sulfur and sulfur dioxide, which are deposited on the surface by volcanic eruptions. Different forms and temperatures of sulfur create the range of hues, from pale yellow to deep red. Against the black sky of space, Io looks almost like a cosmic pizza, splotched and streaked with vibrant colors. The Moon has almost no impact craters because its surface is so young. Any craters that form are quickly buried by fresh lava flows or volcanic ash. Io's appearance is unlike any other world in the solar system, a testament to the power of tidal heating and the dynamic forces that shape its surface every day. Europa may have an ocean twice the size of all of Earth's oceans combined. This moon of Jupiter, slightly smaller than Earth's moon, is covered by a thick shell of water ice. Beneath that shell, scientists believe there is a global ocean of liquid water that could be 100 kilometers deep. Evidence for this ocean comes from several sources: the way Europa's magnetic field interacts with Jupiter's, the moon's smooth, young surface with relatively few craters, and the presence of long cracks and ridges that suggest the ice is floating on top of something liquid. The ocean is kept warm by tidal heating, similar to what happens on Io, but less extreme. Europa's ice shell is estimated to be about 10 to 25 kilometers thick in most places, though it may be thinner near the poles. Beneath this frozen lid, the ocean remains liquid, dark, and potentially teeming with the ingredients necessary for life. Europa's surface is crisscrossed with long, dark lines called lineae. These features can stretch for thousands of kilometers and are thought to be fractures in the ice where warmer material from below has risen to the surface. Some of these cracks are incredibly long, winding across the moon like cosmic highways. The patterns they create suggest that Europa's ice shell is constantly shifting and cracking, perhaps driven by the ocean below or by tidal stresses from Jupiter. The surface is also remarkably smooth, with very few large impact craters, indicating that it is geologically young and constantly being resurfaced. In some regions, the ice appears to have broken apart and refrozen in chaotic jumbles, a terrain scientists call chaos regions. These areas hint at places where the ocean below may have broken through the ice, bringing water to the surface before freezing again. Scientists have detected water vapor plumes erupting from Europa's surface. Observations by the Hubble Space Telescope and data from the Galileo spacecraft suggest that geysers of water vapor occasionally shoot up from Europa's south polar region, reaching heights of over 100 kilometers. These plumes are similar to those seen on Enceladus, Saturn's icy moon, and they offer a tantalizing opportunity to sample the ocean without having to drill through the thick ice shell. If these plumes are confirmed and are indeed connected to the subsurface ocean, future missions could fly through them and analyze their composition directly, searching for signs of organic molecules or other indicators that the ocean might be habitable. Enceladus is a small, icy moon of Saturn that has geysers spewing water and ice into space. This tiny world, only about 500 kilometers across, has become one of the most exciting places in the solar system for the search for life. In 2005, the Cassini spacecraft discovered enormous plumes of water vapor and ice particles erupting from fractures near Enceladus's south pole. These plumes shoot hundreds of kilometers into space at speeds of about 800 miles per hour. The material in the plumes contains not just water, but also salts, silica, carbon dioxide, methane, and complex organic molecules. These are the building blocks of life, and their presence in the plumes suggests that Enceladus's subsurface ocean may have conditions suitable for life as we know it. The geysers on Enceladus come from 4 long fractures called tiger stripes. These parallel cracks, each about 130 kilometers long and about 2 kilometers wide, are warmer than the surrounding terrain and glow faintly in infrared images. Scientists believe that the tiger stripes are fractures that reach down through the ice shell to the liquid ocean below. As Enceladus orbits Saturn, tidal forces cause the fractures to open and close, allowing water from the ocean to escape. When the Moon is farthest from Saturn in its orbit, the plumes are about 4 times brighter than when it is closest, supporting the idea that tidal squeezing controls the eruptions. The material from these plumes does not just fall back to the Moon. Much of it escapes into space, forming a faint ring around Saturn known as the E-ring. Enceladus is, in effect, feeding one of Saturn's rings with its own ocean water. Enceladus has the brightest, most reflective surface in the entire solar system. Its icy exterior reflects nearly 100% of the sunlight that hits it, making it shine like a polished mirror. This high reflectivity, combined with its distance from the sun, means that Enceladus's surface is incredibly cold, about -201 degrees Celsius. The ice is kept so clean and bright because fresh ice particles from the geysers constantly fall back onto the surface like snow, covering older, darker material. The Moon's surface is also remarkably smooth in some areas, with very few craters, suggesting that it has been resurfaced relatively recently by geological activity. In other areas, the surface is heavily fractured and grooved, evidence of tectonic forces at work beneath the ice. Beneath Enceladus's ice shell is a global ocean that may be in contact with a rocky seafloor. Analysis of the particles in the plumes has revealed tiny grains of silica, a mineral that can only form at high temperatures when water interacts with rock. This suggests that Enceladus's ocean is not just sitting beneath the ice, but is actively in contact with the Moon's rocky interior, possibly at hydrothermal vents similar to those found at the bottom of Earth's oceans. These vents could provide heat and chemical energy, creating environments where life might thrive. The combination of liquid water, organic molecules, and a source of energy makes Enceladus one of the most promising places in the solar system to search for life beyond Earth. Triton is Neptune's largest moon and orbits the planet backward. Unlike most large moons, which orbit in the same direction as their planet's rotation, Triton moves in what is called a retrograde orbit. This backward motion is strong evidence that Triton did not form alongside Neptune, but was instead captured by the planet's gravity. Triton is thought to have originated in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit, before being pulled into orbit around the gas giant. This capture would have been a violent event, potentially disrupting other moons that Neptune might have had at the time. Triton's retrograde orbit also means that it is slowly spiraling inward toward Neptune. In a few billion years, it will either collide with Neptune or be torn apart by tidal forces, forming a spectacular ring system around the planet. Triton has geysers of nitrogen gas erupting from its surface. Discovered by Voyager 2 in 1989, these geysers shoot plumes of nitrogen gas and dark dust particles up to 8 kilometers high. The nitrogen exists as ice on Triton's extremely cold surface, which averages about -235 degrees Celsius. When sunlight warms the ice, it sublimates directly into gas, building up pressure beneath the surface until it bursts through in dramatic eruptions. The dark material carried by the plumes may be organic compounds created by radiation processing of methane and nitrogen ices. As the plumes rise and fall, they paint dark streaks across Triton's surface, creating patterns that can be seen from space. Despite being one of the coldest places in the solar system, Triton is geologically active, powered by sunlight rather than internal heat. Triton's surface is geologically young and remarkably varied. It features smooth plains, ridges, and a region called the Cantaloupe Terrain, which is covered in dimples and pits that resemble the skin of a melon. There are also very few impact craters, suggesting that the surface has been resurfaced relatively recently, perhaps within the last few 100 million years. Some scientists think that Triton may have a subsurface ocean beneath its icy shell, kept liquid by tidal heating during its early history, when its orbit was more elliptical. Today, Triton's orbit has circularized, reducing the tidal heating, but the Moon's complex surface hints at a dynamic past and possibly ongoing geological processes. Callisto is the most heavily cratered object in our solar system. This ancient moon of Jupiter is covered with impact craters of all sizes, some overlapping others in dense layers that record billions of years of bombardment. Unlike Europa or Io, Callisto shows little sign of geological activity that might erase these craters. Its surface is dark and heavily scarred, a testament to the violent early history of the solar system, when asteroids and comets were far more numerous. The largest impact basin on Callisto, called Valhalla, is enormous, with concentric rings stretching outward for thousands of kilometers. These rings formed when a massive object struck the Moon, sending shockwaves rippling through the ice and creating a bull's-eye pattern that remains visible today. Callisto may also have a subsurface ocean. Despite its ancient and inactive-looking surface, measurements of Callisto's magnetic field suggest that there may be a layer of salty liquid water buried deep beneath the ice and rock. This ocean would be sandwiched between layers of ice and rock, making it less accessible than the oceans on Europa or Enceladus, but still intriguing. The presence of a subsurface ocean on Callisto would make it another potential ocean world, adding to the growing list of moons where liquid water exists beneath the surface. However, Callisto's ocean, if it exists, is likely very deep and isolated, making it less promising for habitability compared to Europa or Enceladus. Miranda is one of the most bizarre moons in the solar system. Orbiting Uranus, this small moon has a surface that looks like it was assembled from mismatched pieces. There are heavily cratered regions next to smooth plains and enormous cliffs that plunge 15 kilometers deep, making them some of the tallest cliffs in the entire solar system. The surface is crisscrossed with grooves, ridges, and strange polygonal shapes called coronae. Scientists believe that Miranda may have been shattered by a massive impact in its past, and then reassembled under its own gravity, creating the chaotic patchwork we see today. Alternatively, internal heating from tidal forces during a time when Miranda was in an orbital resonance with other Uranian moons may have caused partial melting and resurfacing, creating the varied terrain. Either way, Miranda remains one of the solar system's great mysteries. The moons of Uranus are named after characters from Shakespeare and Alexander Pope. Unlike other planets, whose moons are named after figures from Greek and Roman mythology, Uranus's moons have names like Oberon, Titania, Ariel, Umbriel, Miranda, Puck, and Cordelia. These names come from the works of William Shakespeare and the poem The Rape of the Lock by Alexander Pope. The tradition began with William Herschel, who discovered Uranus and its two largest moons in the late 1700s, and it has continued ever since. The naming convention gives Uranus's moons a unique literary charm, as if they belong to a cosmic theatre where ancient stories play. Out among the stars. Phobos and Deimos are the two small moons of Mars. These tiny, irregularly shaped moons are thought to be captured asteroids that were pulled into orbit around Mars long ago. Phobos, the larger of the two, measures about 22 kilometers across, while Deimos is even smaller at about 12 kilometers. Both moons are dark and heavily cratered, with surfaces covered in a layer of fine dust. Phobos orbits so close to Mars that it completes an orbit in just 7.5 hours, meaning it rises and sets multiple times each Martian day. This close orbit also means that Phobos is slowly spiraling inward toward Mars. In about 50 million years, it will either crash into the planet or be torn apart by tidal forces, forming a ring around Mars. Some moons are tidally locked to their planets, This means they always show the same face to their planet, just as our moon always shows the same side to Earth. Tidal locking occurs when the gravitational interaction between a planet and its moon slows the moon's rotation until it matches its orbital period. Once locked, one hemisphere of the moon perpetually faces the planet, while the other side remains hidden. Many of the large moons in our solar system are tidally locked, including Earth's moon, Jupiter's Galilean moons, and several of Saturn's moons. For observers on the planet, the moon never appears to rotate. For observers on the moon, the planet hangs in the same spot in the sky, never rising or setting. Moons can have their own moons, though none have been confirmed yet. The idea of a moon orbiting another moon, sometimes called a moon-moon or submoon, is theoretically possible, but no such system has been discovered in our solar system. For a moon to have its own moon, it would need to have sufficient gravity to hold onto a smaller object, while also being far enough from its parent planet that the planet's gravity would not disrupt the smaller moon's orbit. Most of the conditions required for this are difficult to meet, which is why moon-moons are likely rare or non-existent. However, the concept remains intriguing to astronomers who study the dynamics of orbital systems. Some moons are covered in a thick layer of dust. Phobos and Deimos, Mars's two small moons, are both coated in a blanket of fine dust that is several meters thick. This dust, called regolith, is created by billions of years of impacts from tiny meteoroids that have pulverized the surface rock. The dust gives the moons a soft, almost powdery appearance in images taken by spacecraft. Similarly, Earth's moon is covered in a layer of regolith created by impacts, and astronauts during the Apollo missions found that the fine lunar dust stuck to everything and was difficult to brush off. Regolith is a common feature on airless bodies throughout the solar system, a testament to the constant bombardment they endure from space debris. Moons can have temporary atmospheres. Some moons, like Io and Europa, have extremely thin atmospheres that are constantly being replenished. Io's atmosphere is made mostly of sulfur dioxide gas that is released by volcanic eruptions and then gradually lost to space. Europa's atmosphere, detected by the Hubble Space Telescope, consists mostly of oxygen, likely produced when radiation from Jupiter breaks apart water molecules on the moon's surface. These atmospheres are so thin that they are more like exospheres, where atoms and molecules rarely collide. They are nothing like Earth's thick, protective atmosphere, but they do exist, creating faint envelopes of gas around these moons. Moons can have magnetic fields. Ganymede is the only moon in the solar system known to have its own global magnetic field, generated by a liquid iron core that acts like a dynamo. This magnetic field creates a small magnetosphere around the moon, a bubble of magnetic influence that interacts with Jupiter's much larger magnetic field. The discovery of Ganymede's magnetic field was surprising because generating a magnetic field requires internal motion and heat, processes more commonly associated with planets than moons. The field is about 1% as strong as Earth's, but it is enough to deflect some of the charged particles streaming from Jupiter, creating auroras near Ganymede's poles. Some moons orbit their planets in just a few hours. The inner moons of Jupiter and Saturn orbit so close to their planets that they complete an orbit in a matter of hours. For example, Metis, one of Jupiter's inner moons, orbits the planet in about 7 hours. These moons are small, irregularly shaped, and orbit within or just outside the planet's ring systems. They move so quickly that from the planet's surface they would appear to zip across the sky. Their rapid orbits also mean they are subject to intense tidal forces, which may shape their structure and, in some cases, cause them to slowly lose material to the rings. Moons can shepherd planetary rings. Some small moons orbit within or near a planet's ring system and use their gravity to keep the ring particles in line. These shepherd moons create gaps in the rings, define their sharp edges, and prevent the rings from spreading out or collapsing. Saturn's rings, for example, have several shepherd moons, including Prometheus and Pandora, which orbit on either side of the narrow F ring. The moon's gravitational influence confines the ring particles, creating the intricate structures we see. Without these shepherd moons, the rings would gradually disperse, losing their distinct boundaries and features. Saturn has more moons than any other planet in the solar system. As of early 2025, Saturn has at least 274 confirmed moons, far more than any other planet. These moons range from enormous Titan, with its thick atmosphere and lakes of methane, to tiny moonlets embedded in Saturn's rings that are barely a few hundred meters across. Some of Saturn's moons are regular, satellites that formed alongside the planet, while others are irregular moons that were captured by Saturn's gravity. The sheer number of moons makes Saturn a miniature solar system in its own right, with a complex family of satellites that interact with each other and with Saturn's rings in fascinating ways. Moons can have subsurface oceans kept warm by tidal heating. Several moons in our solar system, including Europa, Enceladus, Ganymede, and possibly Callisto, are thought to have liquid water oceans beneath their icy surfaces. These oceans are kept from freezing by tidal heating, a process where the gravitational pull of the parent planet flexes the moon's interior, generating heat through friction. This heat is enough to melt ice and maintain liquid water, even though the surface temperatures are far below freezing. The presence of these subsurface oceans makes these moons some of the most promising places to search for life beyond Earth, as liquid water is one of the essential ingredients for life as we know it. Moons can have thick ice shells that protect their oceans. The ice shells on moons like Europa and Enceladus are thought to be tens of kilometers thick, insulating the liquid oceans below from the cold of space. This ice acts as a barrier, keeping the oceans warm and protecting them from radiation and impacts. However, the ice is not static. It is fractured, grooved, and constantly being reshaped by tidal forces and geological activity. In some places, the ice may be thin enough that the ocean water can break through, creating cracks, geysers, or areas where the ice has melted and refrozen. Understanding the thickness and behavior of these ice shells is crucial for planning future missions that might try to reach the oceans below. Some moons are almost perfectly round, while others are highly irregular. Large moons like Ganymede, Titan, and Callisto are round because their gravity is strong enough to pull them into a spherical shape, a state called hydrostatic equilibrium. Smaller moons, especially those less than a few hundred kilometers across, often have irregular, potato-like shapes because their gravity is too weak to overcome the structural strength of their rock and ice. Moons like Phobos, Deimos, and many of Jupiter's and Saturn's outer moons are lumpy and misshapen, reflecting their modest size and possibly their origin as captured asteroids or fragments from larger bodies. Moons can have geysers that reach thousands of kilometers into space. The geysers on Enceladus are particularly impressive, shooting plumes of water vapor and ice particles hundreds of kilometers above the surface. In some cases, the James Webb Space Telescope has observed plumes extending up to 6,000 miles, or nearly 10,000 kilometers, creating a massive cloud of water in space. These plumes feed Saturn's E-ring, which is made mostly of ice particles shed by Enceladus. The power and persistence of these geysers suggest that the subsurface ocean is being actively heated and pressurized, likely by tidal forces, and that water from the ocean is finding pathways to the surface through cracks in the ice. Some moons are so small they were only discovered in the last few decades. Advances in telescope technology and spacecraft missions have revealed hundreds of small moons that were previously unknown. Many of Jupiter's and Saturn's moons were discovered by the Voyager and Cassini missions, while others were found using ground-based telescopes and the Hubble Space Telescope. These tiny moons, often just a few kilometers across, orbit far from their planets in irregular, elongated paths, suggesting they are captured asteroids or fragments from collisions. Each new discovery adds to our understanding of the solar system's complexity and the diversity of objects that inhabit it. Moons can influence each other's orbits. In the Jupiter system, the moons Io, Europa, and Ganymede are locked in what is called a Laplace resonance. For every one orbit that Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This precise synchronization means that the moons line up in the same configuration at regular intervals, creating predictable gravitational interactions. These interactions help maintain Io's elliptical orbit, which in turn drives the tidal heating that powers its volcanic activity. Similar resonances exist among some of Saturn's moons, and these gravitational dances play a key role in shaping the evolution and behavior of moon systems. Some moons have surfaces that are billions of years old. Callisto's heavily cratered surface is thought to be among the oldest in the solar system, dating back over 4 billion years. Because Callisto lacks significant geological activity, its surface has remained largely unchanged since the era of heavy bombardment, when the solar system was filled with debris from its formation. Looking at Callisto is like looking back in time to the chaotic early days of the solar system. Other moons, like Europa and Enceladus, have much younger surfaces because geological processes have erased older features, replacing them with fresh ice and new terrain. Moons can have colors that reveal their composition. Io's yellows, oranges, and reds come from sulfur compounds deposited by volcanoes. Europa's surface is mostly white ice with brownish streaks that may contain salts and organic material brought up from the ocean below. Titan's atmosphere gives it a hazy orange appearance due to complex organic molecules called tholins. Enceladus is brilliantly white because of its fresh, clean ice. Callisto is dark and brownish, covered in ancient, weathered material. By studying the colors and spectra of moonlight, scientists can learn what these moons are made of and how their surfaces have evolved over time. Moons can have cliffs and mountains taller than those on Earth. Miranda's cliffs, called Verona Rupes, plunge about 15 kilometers from top to bottom, making them some of the tallest cliffs in the solar system. If you stood at the top and jumped, you would fall for about 12 minutes before reaching the bottom, assuming you could survive the landing. Io has mountains that rise over 17 kilometers high, taller than Mount Everest, formed by the constant compression of the crust as lava flows pile up and push the surface upward. These towering features remind us that moons are not just small, insignificant rocks, but worlds with dramatic topography and landscapes that rival or exceed those on Earth. Some moons have ice that comes in exotic forms. Under the extreme pressures and temperatures inside large moons like Ganymede and Callisto, water ice can exist in forms that do not occur naturally on Earth. These high-pressure ices, with names like Ice 5, Ice 6, and Ice 7, have crystal structures different from the ordinary ice we are familiar with. They can be denser and more rigid, and they may play a role in the internal structure of these moons, separating the rocky core from the liquid ocean and the outer ice shell. Understanding these exotic ices is important for modeling the interiors of large moons and predicting their behavior over time. Moons can have reddish streaks and patches caused by radiation. When charged particles from a planet's magnetosphere strike the surface of a moon, they can break apart molecules and create chemical reactions. On Europa, for example, radiation from Jupiter bombards the surface, breaking apart water ice and creating oxygen and other compounds. The reddish-brown materials seen in Europa's cracks and chaos regions may be salts or organic compounds that have been altered by radiation. Similarly, Ganymede and Callisto show signs of radiation processing, with darker and lighter regions that reflect differences in ice composition and exposure to radiation. This radiation also poses a challenge for any future missions that might try to land on these moons, as the surface is constantly bathed in harmful particles. Some moons are slowly being pulled apart by tidal forces. Phobos, Mars's larger moon, is gradually spiraling inward toward the planet. Eventually, in about 50 million years, it will cross the Roche limit, the distance at which tidal forces from Mars will become strong enough to tear Phobos apart. When this happens, the fragments will spread out into a ring around Mars, creating a temporary ring system. Triton, orbiting Neptune, is also being pulled inward by tidal forces and will eventually meet a similar fate. These processes are slow on human timescales, but inevitable on cosmic ones, reminding us that moons, like everything else in the universe, are not eternal. Moons can have ice that is harder than rock. At the extremely cold temperatures found on the outer moons, water ice becomes as hard and durable as rock on Earth. On Titan, for example, water ice forms the mountains, cliffs, and bedrock of the down landscape. This ice does not melt or flow like ice on Earth. Instead, it remains solid and strong, shaping the surface over billions of years. Methane and other hydrocarbons play the role on Titan that water plays on Earth, flowing in rivers, pooling in lakes, and evaporating into the atmosphere. It is a world where ice is rock and liquid methane is water, a strange inversion of the familiar. Some moons have organic molecules that are the building blocks of life. The plumes of Enceladus contain complex organic molecules, including compounds with carbon, hydrogen, nitrogen, and oxygen. These are the same types of molecules that, on Earth, are essential for life. Similarly, Titan's atmosphere is rich in organic chemistry, with methane and nitrogen combining under the influence of sunlight to form a smog of complex hydrocarbons. These organic materials rain down onto Titan's surface, accumulating over time and creating a rich chemical environment. While the presence of organic molecules does not mean life exists, it does show that the ingredients for life are common in the solar system, and that chemical complexity can arise in many different environments. Moons can have day lengths that differ greatly from their orbital periods. While many moons are tidally locked and have day lengths that match their orbital periods, meaning one side always faces the planet, smaller, irregular moons may tumble as they orbit, experiencing chaotic day-night cycles. For example, Hyperion, a moon of Saturn, rotates chaotically due to its irregular shape and the gravitational influences of nearby Titan. This means that sunrise and sunset on Hyperion are unpredictable, and the moon never settles into a regular rotation. For any future explorers of such moons, this would create a constantly shifting environment, where the sun's position in the sky changes in unexpected ways. Some moons have been visited by spacecraft multiple times. Europa, Io, Ganymede, and Callisto were all studied extensively by the Galileo spacecraft, which orbited Jupiter from 1995 to 2003. Enceladus was observed by the Cassini spacecraft during multiple flybys between 2005 and 2017. Titan was visited by both the Cassini orbiter and the Huygens lander, which touched down on its surface in 2005. These missions have transformed our understanding of these moons, revealing active geology, subsurface oceans, and complex chemistry. Future missions, like NASA's Europa Clipper and the European Space Agency's JUICE mission, will continue this exploration, seeking to answer the question of whether life exists on any of these distant worlds. Moons can have nights that last for weeks or even months. On moons that are tidally locked to their planets but orbit far from the Sun, the night side can remain in darkness for long periods. For moons in the outer solar system, where sunlight is already faint, this darkness is profound. On Titan, single day and night cycle lasts about 16 Earth days, and the thick atmosphere diffuses what little light reaches the surface. On Triton, the combination of Neptune's weak sunlight and the Moon's own orbit creates conditions where some regions remain in shadow for extended periods. These long nights, combined with extreme cold, create environments utterly unlike anything on Earth. Some moons are named after mythological figures. Most of the moons in our solar system are named after gods, goddesses, and other figures from Greek and Roman mythology. Jupiter's moons are named after lovers and descendants of the god Jupiter. Saturn's moons are named after titans and other figures from Greek mythology. Neptune's moons are named after sea gods and nymphs. This tradition gives the moons poetic and evocative names that reflect humanity's long history of storytelling and our connection to the night sky. Moons can have surfaces that glow faintly in the dark. Some moons, like Europa and Ganymede, may have surfaces that emit a faint glow when bombarded by radiation from their parent planet. This phenomenon, called ice luminescence, occurs when high-energy particles strike the ice and excite the molecules, causing them to emit light. The glow would be too faint to see with the naked eye, but it has been detected in laboratory experiments and may occur naturally on the icy moons of the outer solar system. This subtle luminescence adds another layer of mystery and beauty to these distant worlds. The smallest known moons are just a few kilometers across. Some of the tiny moons orbiting Jupiter and Saturn are barely larger than small mountains. They are irregularly shaped, heavily cratered, and likely fragments from larger bodies that were broken apart by collisions. These moonlets are difficult to study because of their small size, but they provide clues about the history of the solar system and the processes that shape planetary systems. Each one is a world in miniature, a fragment of cosmic history floating in the darkness. Moons can have retrograde orbits. In addition to Triton, several other moons in the solar system orbit in the opposite direction of their planet's rotation. These retrograde moons are typically small and irregular, and they orbit far from their planets. They are thought to be captured objects, originally asteroids or Kuiper belt objects, that wandered too close to a planet and were pulled into orbit. Their backward motion marks them as outsiders, travelers who found a new home far from where they began. Some moons have surfaces shaped by tectonic forces. Europa's long cracks and ridges are evidence of tectonic activity driven by tidal forces. As the Moon orbits Jupiter, the changing gravitational pull causes the ice shell to flex and crack, creating the linear features we see on the surface. Similarly, Enceladus's tiger stripes are thought to be tectonic fractures where the ice has been pulled apart by tidal stresses. These tectonic processes are different from those on Earth, where plate tectonics are driven by mantle convection, but they are no less dramatic in their effects. Moons can have seas that are larger than some of Earth's lakes. Titan's Kraken Mare, the largest known body of liquid on the Moon, covers an area larger than the Caspian Sea. Ligeia Mare, Titan's second largest sea, is comparable in size to Lake Superior. These methane seas are deep enough that submarines have been proposed as a way to explore them. Beneath the surface of these seas, there may be currents, tides, and perhaps even dissolved organic material. Exploring Titan's seas would be one of the most exciting and challenging endeavors in planetary science. Some moons have been the subject of intense scientific debate. Europa, in particular, has sparked decades of discussion about whether it might harbor life. The evidence for a subsurface ocean, combined with the detection of organic molecules and the possibility of hydrothermal vents on the ocean floor, makes it a prime target for astrobiological study. Similarly, Enceladus's geysers and the complex chemistry they reveal have led scientists to consider it one of the best places in the solar system to search for life. These debates drive the design of future missions and shape our understanding of what life needs to survive. Moons can have shadows that are incredibly dark. Without an atmosphere to scatter light, the shadows on airless moons are pitch black. On Earth's moon, astronauts found that stepping from sunlight into shadow was like stepping into a void, with no ambient light to ease the transition. The same is true on other airless moons like Io, Callisto, and Phobos. This stark contrast between light and dark creates dramatic landscapes where features are sharply defined and shadows are absolute. Some moons have been proposed as targets for future human exploration. While Mars often dominates discussions of human space exploration, some scientists have suggested that moons like Titan, Europa, or Enceladus could also be destinations for future missions. Perhaps robotic missions first, and then eventually crewed missions. The presence of resources like water ice and organic materials makes these moons potentially valuable for supporting long-term exploration. However, the challenges are immense, including vast distances, extreme cold, high radiation, and the difficulty of landing on icy surfaces or beneath thick ice shells. Moons can have landscapes that change over time. Io's surface is constantly being reshaped by volcanic eruptions. Europa's ice shell cracks and reforms as the moon flexes in its orbit. Enceladus's south pole is continuously venting material from below, creating fresh deposits of ice. Even on quieter moons, impacts from meteoroids slowly alter the surface, adding new craters and churning up the regolith. These changes happen slowly by human standards, but over millions or billions of years, they transform the appearance of these worlds. Moons can have rings of their own. While no moon in our solar system currently has a confirmed ring system, some models suggest that Rhea, one of Saturn's moons, may once have had a faint ring, or may still have one today. The evidence is inconclusive, but if confirmed, it would make Rhea the only moon known to have rings. The rings would be made of dust and ice particles, and would likely be much fainter than Saturn's spectacular ring system. The idea of a moon with rings challenges our traditional categories and reminds us that the solar system is full of surprises. Moons can have craters with bright rays extending outward. When a meteoroid strikes the surface of an airless moon, it creates a crater and ejects material that spreads outward in bright streaks called rays. These rays can extend for hundreds or even thousands of kilometers, creating patterns that are visible from space. Ganymede and Callisto both have large craters with prominent ray systems, evidence of relatively recent impacts. The brightness of the rays gradually fades as the material is darkened by radiation and covered by newer deposits, so bright rays indicate young craters. Some moons are the subject of myths and legends. Earth's moon has inspired countless stories, from ancient tales of moon gods and goddesses to modern science fiction about lunar colonies and adventures. Similarly, the names of other moons evoke the rich mythology of ancient cultures, connecting our exploration of the solar system to humanity's oldest stories. Each time we learn something new about a moon, we add another chapter to this ongoing narrative, blending science and storytelling in a way that enriches both. Moons can have thin, temporary rings of dust. Some of Jupiter's inner moons, like Thebe and Amalthea, are surrounded by faint rings of dust created by meteoroid impacts on their surfaces. When a meteoroid strikes, it kicks up material that briefly orbits the moon before settling back down or escaping into space. These dust rings are much fainter than planetary rings, but they are another example of the dynamic interactions between moons, meteoroids, and their environments. Moons can have internal oceans that are layered. On some large moons, the internal structure may include multiple layers of ice and water. Ganymede, for example, is thought to have several oceans sandwiched between layers of different types of ice. The pressure and temperature at different depths create conditions where water freezes into high-pressure ices, separating one layer of liquid water from another. This layered structure is complex and not fully understood, but it has important implications for the moon's geology, heat flow, and potential habitability. Moons can have surfaces that are soft and powdery. The regolith on some moons is so fine and loosely packed that it behaves almost like a powder. On Earth's moon, astronauts found that their boots sank several centimeters into the regolith with each step. The lack of moisture and the constant bombardment by micrometeorites create a surface that is both soft and abrasive, clinging to spacesuits and equipment. Future missions to other moons will need to account for the properties of their regoliths, which can vary widely depending on the moon's composition and history. Some moons have been the inspiration for works of art and literature. From H.G. Wells's First Men in the Moon to Arthur C. Clarke's exploration of Europa in 2001, A Space Odyssey, moons have captured the imagination of writers, artists, and filmmakers. These creative works reflect our fascination with these distant worlds and our desire to explore them, even if only in our imaginations. They also inspire real scientific exploration, as the questions posed in fiction often drive the questions we ask in science. Moons can have gravity so weak that a person could easily jump into orbit. On tiny moons like Deimos, which is only about 12 kilometers across, the escape velocity is so low that a person could theoretically jump fast enough to leave the moon entirely. The gravity is so gentle that objects would fall in slow motion, and throwing a ball would send it on long, arcing trajectories that might take minutes to complete. For astronauts exploring such moons, tethers and anchors would be essential to avoid accidentally floating away into space. These tiny worlds challenge our understanding of what it means to be on solid ground, where the distinction between standing and floating becomes blurred. Some moons have surfaces made of materials that would feel slushy or crunchy. The regolith on many moons is not like soil on Earth. It is often extremely fine, like powder, but it can also contain larger chunks and fragments. On Titan, where temperatures are so cold that methane is liquid, the surface might include areas of frozen methane that would crunch underfoot, mixed with water ice that is as hard as concrete. On Europa, if you could walk on the surface, you might encounter ridges of ice that have buckled and refrozen into jagged formations. Each moon's surface would have its own unique texture, determined by its composition, temperature, and geological history. Moons can have magnetic fields that are induced by their parent planets. Europa and Callisto both show evidence of induced magnetic fields, created when Jupiter's powerful magnetic field sweeps past them and interacts with conductive layers inside the moons. In Europa's case, this conductive layer is thought to be the salty ocean beneath the ice. The induced field is much weaker than Jupiter's own field, but it is strong enough to be measured by spacecraft and provides important evidence for the existence of subsurface oceans. This magnetic interaction is a subtle but powerful tool for understanding the internal structure of moons. Some moons have surfaces that are covered in grooves and ridges. Ganymede's surface, for example, marked by long parallel grooves that stretch for hundreds of kilometers. These grooves are thought to have formed when the moon's icy crust was stretched and fractured, possibly by tectonic forces or changes in the internal structure. Similarly, Enceladus's surface has grooves and cracks that crisscross the terrain, evidence of the tidal forces that flex and shape the moon. These features give the surfaces a distinctive, almost sculptured appearance, as if the ice has been carefully carved by invisible hands. Moons can have regions that are geologically dead alongside regions that are active. Ganymede is a perfect example of this contrast. Parts of the moon are covered in ancient, heavily cratered terrain that has remained unchanged for billions of years. Other parts are much younger, with smooth plains and grooved terrain that formed more recently. This patchwork of old and new suggests that Ganymede's geological activity has been sporadic, with periods of resurfacing separated by long stretches of dormancy. It is as if the moon's heart beats irregularly, waking occasionally to reshape the surface before falling quiet again. Some moons are so far from the sun that sunlight is extremely faint. On Triton, which orbits Neptune at a distance of about 4.5 billion kilometers from the sun, sunlight is about 900 times weaker than it is on Earth. Noon on Triton would feel more like twilight, with the sun appearing as a very bright star rather than a blazing disk. Shadows would be softer, and colors would be muted. Yet even in this dim light, Triton's nitrogen ice can sublimate and create geysers, proving that even faint sunlight can drive geological processes. Moons can have craters filled with ice. On Ganymede and Callisto, many craters have bright white floors, suggesting they are filled with relatively pure water ice. These icy deposits may have formed when impacts excavated deeper, cleaner ice, or when water seeped up from below and froze in the crater basin. On Enceladus, craters are rare because the surface is so young, but those that do exist are often partially filled with fresh ice from the ongoing resurfacing. These ice-filled craters create a distinctive contrast with the darker, more weathered terrain around them. Some moons have polar regions that are much warmer than expected. Enceladus's south pole, for example, is warmer than the rest of the moon, with temperatures reaching about -93 degrees Celsius, compared to -200 degrees Celsius elsewhere. This warmth is caused by the tidal heating that powers the geysers in the tiger stripe fractures. Similarly, Io's poles show higher temperatures than other regions, possibly due to volcanic activity or the concentration of sulfur dioxide frost, which has different thermal properties than the surrounding materials. These warm spots are clues to the internal processes that shape these moons. Moons can have surfaces that are incredibly smooth. Parts of Europa are among the smoothest surfaces in the solar system, with very few craters and almost no large-scale topography. The smoothness suggests that the surface has been resurfaced recently, either by the upwelling of material from below or by the flexing and cracking of the ice shell. On Enceladus, the regions near the South Pole are also remarkably smooth, with the fresh ice from the geysers covering older features. These smooth areas are like blank canvases, erasing the past and presenting a fresh surface to the cosmos. Some moons have orbits that are so elliptical they experience extreme variations in distance from their planet. Nereid, a moon of Neptune, has one of the most elliptical orbits of any large moon in the solar system. Its distance from Neptune varies from about 1.4 million kilometers at its closest to over 9.6 million kilometers at its farthest. This extreme ellipticity suggests that Nereid may have been captured by Neptune's gravity, or had its orbit severely disrupted by some past event. The moon's journey around Neptune takes it through vastly different environments, from the intense gravitational influence close to the planet to the quiet isolation of the outer reaches. Moons can have surfaces that look like fractured glass. When ice on a moon's surface is subjected to stress, it can crack in patterns that resemble shattered glass. Europa's surface shows many such patterns, with networks of cracks spreading across the ice like a spider's web. These fractures form when the ice shell is pulled and twisted by tidal forces, or when the surface expands and contracts due to temperature changes. The result is a landscape that looks delicate and fragile, even though the ice is actually quite thick and strong. Some moons have been the target of proposed sample return missions. Scientists have long dreamed of bringing back samples from moons like Europa, Enceladus, or Titan. Such a mission could collect ice from Europa's surface, scoop up plume material from Enceladus, or gather sediment from Titan's lakes. Analyzing these samples in laboratories on Earth would provide far more detailed information than any spacecraft instrument could, potentially revealing the presence of organic molecules, isotopic ratios, and other clues about the moon's history and potential for life. While no such mission has yet launched, the technology and plans are being developed, and a sample return mission could become reality within the next few decades. Moons can have surfaces that are younger than the age of the solar system. While the solar system itself is about 4.6 billion years old, many moons have surfaces that are much younger. Europa's surface, for example, is thought to be only about 60 million years old, meaning it has been completely resurfaced in geologically recent times. Enceladus's surface near the South Pole may be even younger, perhaps only a few tens of millions of years old. These young surfaces tell us that these moons are geologically active today, constantly renewing themselves and erasing the scars of the past. Some moons have been the subject of proposals for floating probes. Titan's methane seas have inspired concepts for floating probes that could splash down on the surface and drift across the liquid, taking measurements and sending back data. Such a probe would need to withstand extremely cold temperatures and navigate using radar or other instruments, as the thick atmosphere blocks most visible light. The idea of sailing on an alien sea captures the imagination and represents one of the most exciting possibilities for future exploration. NASA's proposed Titan Mara Explorer mission would have been the first such endeavor, though it has not yet been funded. Moons can have atmospheres that extend far beyond their surfaces. Io's atmosphere, though very thin, extends several hundred kilometers above the surface, forming a tenuous envelope around the moon. This atmosphere is constantly being replenished by volcanic eruptions and constantly being lost to space, creating a dynamic balance. Similarly, Enceladus's plumes create a temporary atmosphere around the moon, as water vapor and ice particles are ejected and then fall back or escape. These extended atmospheres blur the boundary between the moon and space, creating a transition zone rather than a sharp edge. Some moons have light and dark hemispheres. Iapetus, a moon of Saturn, has one of the most striking appearances of any moon in the solar system. One hemisphere is covered in bright, clean ice, while the other is coated in dark, reddish material. This two-toned appearance is thought to result from a combination of processes. Dark material may have been deposited from outside, perhaps from a distant moon or from Iapetus's own orbit through Saturn's dusty ring system. And then, the sun's heat caused the dark material to sublimate ice on the dark side, leaving behind even more dark residue. The bright side remains clean because it reflects so much sunlight that ice does not sublimate. The result is a moon that looks like it has been painted half black and half white. Moons can have surfaces that are covered in fine frost. On many cold moons, volatile materials like carbon dioxide, nitrogen, or methane can condense out of the thin atmosphere and coat the surface in a layer of frost. This frost can be very fine, almost like snow, and it can change with the seasons or with the moon's position in its orbit. On Triton, for example, the nitrogen frost that covers much of the surface can sublimate and refreeze, creating a constantly shifting landscape. The frost gives these moons a delicate, ethereal appearance, as if they are covered in a blanket of frozen mist. Some moons have been observed changing in real time. When Voyager 1 and Voyager 2 flew by Jupiter in 1979, they took images of Io 4 months apart. Comparing the images revealed that several volcanic plumes had started or stopped erupting in that short time, and that lava flows had altered the surface. This was the first direct observation of geological change on another world, and it demonstrated just how active Io is. Since then, ground-based telescopes and spacecraft have continued to monitor Io, tracking the rise and fall of volcanic activity and mapping the changes to the surface. Moons can have names that reflect their place in the planet's family. The Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, were among the first moons discovered beyond Earth, observed by Galileo Galilei in 1610. Their names come from figures in Greek mythology who were associated with the god Zeus, the Greek equivalent of Jupiter. This naming tradition has been extended to Jupiter's many other moons, each named after a different figure from mythology. The names give each moon a sense of identity and history, connecting them to the stories humans have told for thousands of years. Some moons have surfaces that are covered in small, rounded pebbles. In some regions of Titan, the Huygens lander observed a surface covered in smooth, rounded objects that looked like pebbles or cobbles. These may be made of water ice, which is as hard as rock at Titan's temperatures, and they may have been rounded by the action of flowing methane or by some other erosion process. The presence of these pebbles suggests that Titan's surface is shaped by processes similar to those on Earth, where rivers and streams round and smooth stones over time. Moons can have gravity that varies across their surface. Because many small moons are irregularly shaped, their gravity is not uniform. Near a large mountain or a dense region of rock, the gravitational pull would be slightly stronger than in other areas. This variation is usually very small, but it could be detected by sensitive instruments and might affect the trajectories of spacecraft or the behavior of dust and debris on the surface. On larger, more spherical moons, the gravity is more uniform, but even there, differences in internal structure can create subtle variations in the gravitational field. Some moons have been the sites of proposed human habitats. Scientists and engineers have speculated about building bases on moons like Europa, Enceladus, or Titan, where resources like water ice and organic materials are abundant. These bases could use in situ resource utilization to produce fuel, oxygen, and building materials, reducing the need to transport everything from Earth. However, the challenges are immense. The extreme cold, high radiation, lack of breathable air, and vast distances would make such bases extremely difficult to build and maintain. Still, the idea of establishing a human presence on a distant moon captures the imagination and represents a long-term goal for space exploration. Moons can have surfaces that are shaped by sublimation. Sublimation is the process by which a solid turns directly into a gas without passing through a liquid phase. On cold moons, ices of water, carbon dioxide, nitrogen, and methane can sublimate when warmed by sunlight or internal heat. This sublimation can carve pits, grooves, and other features into the surface, creating a landscape that looks like it has been eaten away. On Triton, sublimation is thought to be responsible for some of the unusual terrain, including pitted plains and smooth areas where volatile ices have been removed. Some moons have been observed to have changing brightness over time. As a moon orbits its planet and rotates, different parts of its surface face the sun, causing its overall brightness to change. These brightness variations can reveal information about the moon's shape, surface features, and composition. For example, Iapetus's brightness changes dramatically as it orbits Saturn, appearing much brighter when the icy hemisphere faces us and much dimmer when the dark hemisphere is visible. By monitoring these changes over time, astronomers can learn about the distribution of materials on the moon's surface and how they interact with sunlight. Moons can have surfaces that are covered in boulders. Some moons, especially smaller ones that have experienced impacts or tectonic activity, have surfaces littered with large boulders. These boulders can be fragments of rock or ice that were broken off by impacts or that tumbled down slopes from higher terrain. On Enceladus, the regions near the tiger stripes are covered in house-sized blocks of ice, likely created by the tectonic forces that opened the fractures. These boulders create a rough, jumbled landscape that would be difficult to navigate. Some moons have thin layers of dust on top of ice. On many icy moons, a thin layer of dust and dark material covers the bright ice beneath. This dust may come from impacts, which kick up material from below, or from deposits carried by the planet's magnetosphere or by infalling debris from space. Over time, radiation and micrometeorite impacts can darken this dust layer, making the surface appear older and more weathered than the ice beneath. Removing just a thin layer of this dust would reveal the bright, clean ice below, as if peeling back a curtain to reveal the moon's true face. Moons can have orbital periods that are measured in Earth years. Some of the outer moons of Jupiter and Saturn orbit so far from their planets that they take many Earth years to complete a single orbit. For example, some of Jupiter's irregular moons have orbital periods of over 700 Earth days, while some of Saturn's most distant moons take even longer. These slow orbits mean that the moons spend long stretches in different regions of their planet's magnetosphere and experience gradually changing conditions as they make their way around their immense paths. Some moons have been imaged at resolutions high enough to see features just a few meters across. During close flybys, spacecraft like Cassini and Galileo have captured images of moons like Enceladus and Europa with such high resolution that individual boulders, cracks, and small craters are visible. These detailed images reveal the texture and structure of the surface in ways that were impossible before the space age. They show that these moons are not smooth and featureless, but are covered in intricate details that tell stories of impacts, tectonic activity, and other processes. Moons can have day sides and night sides with vastly different temperatures. On tidally locked moons, one side perpetually faces the planet, while the other faces away. On airless moons, the temperature difference between these two sides can be extreme. The side facing the planet may receive reflected sunlight and heat, keeping it slightly warmer, while the far side remains in deep cold. On Io, The day side can reach temperatures high enough to melt sulfur, while the night side is frigid. These temperature gradients drive heat flow and may influence geological processes. Some moons have been the subject of intense scientific study for decades. Europa, in particular, has been studied by astronomers, planetary scientists, and astrobiologists for over 40 years. The discovery of its subsurface ocean in the late 1990s transformed it from a curious moon into one of the most important targets for the search for life. Since then, every new observation and every new model has added to our understanding of this enigmatic world. Europa represents the culmination of decades of scientific effort, and the hope that we may one day answer the question of whether life exists beyond Earth. Moons can have surfaces that preserve the record of the solar system's history. Because many moons have no atmosphere and little geological activity, their surfaces act as archives, preserving craters and features from billions of years ago. By studying the number and size distribution of craters, scientists can estimate the age of different regions and learn about the history of impacts in the solar system. These ancient surfaces are like pages in a book, each crater a chapter that tells a story about the moon's past and the environment it has endured. Moons can have storms and winds, even without thick atmospheres. On Io, the volcanic plumes create localized disturbances in the thin atmosphere, moving gases and dust across the surface. On Triton, the nitrogen geysers carry dark material that settles in streaks shaped by the moon's thin atmosphere and the faint winds that blow across its surface. Even on Enceladus, where the atmosphere is extremely tenuous, the eruption of geysers creates brief, localized gusts as material escapes into space. These processes are not weather in the traditional sense, but they are dynamic and atmospheric in their own way. Some moons have been found to have complex internal structures. Ganymede, for instance, is thought to have a layered interior that includes an iron core, a rocky mantle, and multiple layers of ice and liquid water. This complex structure rivals that of terrestrial planets and challenges our understanding of how such intricate arrangements can form and persist. The presence of multiple ice layers, each with different crystal structures due to varying pressure and temperature, adds even more complexity. Understanding these internal structures requires careful analysis of gravitational data, magnetic field measurements, and theoretical models that take into account the physics of ice under extreme conditions. Moons can have features that are named after explorers and scientists. Many features on moons are named in honor of people who have contributed to our understanding of the solar system. On Europa, for example, craters and other features are named after Celtic myths and gods. On Titan, mountains, lakes, and regions are named after mythological locations and characters. The naming of these features is overseen by the International Astronomical Union, which ensures that names are appropriate and follow established conventions. These names help us navigate and discuss these distant landscapes, giving them a sense of familiarity even though they are millions of kilometers away. Some moons have been observed to have auroras. Ganymede, with its own magnetic field, experiences auroras near its poles, when charged particles from Jupiter's magnetosphere interact with the moon's atmosphere. These auroras are similar to Earth's northern and southern lights, but they are much fainter and occur in different wavelengths. The Hubble Space Telescope has captured images of these auroras, which appear as glowing bands near the poles. Studying Ganymede's auroras provides insights into the moon's magnetic field, its interaction with Jupiter, and the composition of its thin atmosphere. Moons can have surfaces that are shaped by impacts of comets and asteroids. Over billions of years, countless objects have collided with moons, creating craters of all sizes. Large impacts can excavate deep basins and eject material that travels hundreds or thousands of kilometers before settling back down. Some of this ejecta can even escape the Moon entirely, becoming part of the interplanetary environment. The patterns of craters on a Moon's surface tell us about the history of impacts in the solar system and how the rate of impacts has changed over time. They also reveal information about the Moon's strength and composition, as different materials respond to impacts in different ways. Some moons have been the subject of long-duration spacecraft missions. The Cassini mission, for example, orbited Saturn for over 13 years, from 2004 to 2017, and made dozens of close flybys of Saturn's moons. During this time, Cassini observed seasonal changes on Titan, discovered the geysers on Enceladus, and studied the complex interactions between the moons and Saturn's rings. The wealth of data collected by Cassini has transformed our understanding of the Saturnian system and has provided a detailed record of how these moons behave over time. Moons can have surfaces that glow in ultraviolet light. When the Hubble Space Telescope and other ultraviolet observatories look at moons, they sometimes see them glowing in ways that are invisible to the naked eye. This glow can come from several sources, including auroras, fluorescence from certain minerals, or the scattering of sunlight by the thin atmosphere or surface materials. Europa, for example, shows a faint ultraviolet glow that may be related to the interaction between Jupiter's radiation and the Moon's icy surface. These ultraviolet observations provide additional information about the composition and behavior of moons that complements what we learn from visible and infrared observations. Some moons have been discovered by amateur astronomers using backyard telescopes. While most moons are discovered by professional astronomers using powerful telescopes or by spacecraft, a few have been found by dedicated amateurs who spend countless hours scanning the skies. These discoveries are rare, as modern professional surveys are very thorough, but they serve as a reminder that exploration is not limited to those with access to the largest instruments. The discovery of a new moon, even a tiny one, is a significant contribution to our knowledge of the solar system. Moons can have surfaces that are covered in ridges that look like waves frozen in time. On Europa and Ganymede, some regions are marked by parallel ridges that resemble the ripples on a body of water. These ridges may have formed when the icy crust was compressed or stretched by tidal forces, causing it to buckle and fold. The spacing and orientation of the ridges provide clues about the stresses that shaped them and the properties of the ice at the time they formed. From a distance, these ridged terrains look almost like a frozen sea, captured mid-wave and held in place for millions of years. Some moons have been proposed as locations for telescope observatories. The far side of Earth's moon, for instance, is an excellent location for a radio telescope because it is shielded from the radio noise generated by Earth. Similarly, some scientists have suggested that other moons, particularly those with stable surfaces and low gravity, could host telescopes or other scientific instruments. These observatories could study the cosmos in ways that are difficult or impossible from Earth or from space-based platforms. While such projects are still in the conceptual stage, they represent one of the many potential uses for moons in future exploration. Moons can have surfaces that are covered in materials transported from other bodies. Some of the dust and particles on a moon's surface may not have originated there, but instead came from other moons, from the planet, or even from interplanetary space. For example, material from Io's volcanoes can end up on the moon's surfaces of Europa, Ganymede, and Callisto, carried by Jupiter's magnetosphere. Similarly, particles from Enceladus's plumes can coat other moons in the Saturn system. This transfer of material creates a kind of cosmic mixing, where the surfaces of moons become blends of local and imported materials. Some moons have been observed to have changing surface features. On Io, new volcanic features appear and old ones fade as lava flows cover the surface. On Europa, the cracks and ridges suggest that the ice shell is constantly shifting and breaking. Even on quieter moons, subtle changes can occur over time as impacts add new craters or as frost migrates from one region to another. These changes are usually very slow by human standards, but over the lifespan of a moon, they can completely transform the landscape. Moons can have regions that are brighter or darker than others. These variations in brightness, called albedo variations, can reveal differences in composition, age, or weathering. Bright regions may be covered in fresh ice or frost, while dark regions may contain older, more weathered material or deposits of organic compounds. On Titan, for example, the bright regions are thought to be areas where methane rain has washed away dark organic material, while the dark regions are equatorial deserts covered in hydrocarbon sand dunes. These brightness patterns help scientists map the distribution of materials on a moon's surface. Some moons have been the subject of proposals for nuclear-powered drilling missions. One of the most ambitious ideas for exploring moons like Europa is to send a nuclear-powered probe that could melt its way through the ice shell and reach the ocean below. This cryobot would carry instruments to study the ice as it descends, and would deploy a small submarine or hydrobot to explore the ocean. Such a mission would face enormous technical challenges, including ensuring that the probe does not contaminate the ocean with Earth microbes, and designing systems that can operate autonomously in an environment that is completely unknown. Despite these challenges, the potential scientific rewards make this an attractive concept for future exploration. Moons can have surfaces that are covered in banded terrain. Some moons, like Europa and Ganymede, have regions where the surface is marked by parallel bands of alternating bright and dark material. These bands are thought to form when the icy crust cracks and separates, allowing darker material from below to well up and fill the gap. Over time, these bands can become very wide, creating a striped appearance. The orientation and spacing of the bands provide clues about the tectonic forces that shaped the surface and the properties of the ice and underlying materials. Some moons have been observed by multiple spacecraft from different angles. By combining observations from different missions, scientists can build up a more complete picture of a moon's surface and environment. For example, both Voyager and Cassini imaged Saturn's moons, but from different distances and with different instruments, allowing scientists to see features at multiple scales and in different wavelengths. Similarly, the Galileo and Juno missions have both studied Jupiter's moons, providing complementary data that enhances our understanding. These multi-mission observations are essential for piecing together the complex stories of these distant worlds. Moons can have orbits that are influenced by resonances with other moons. When two or more moons orbit a planet, their gravitational interactions can cause their orbits to become synchronized in specific ratios. These orbital resonances can be very stable and can persist for billions of years. They can also lead to increased tidal heating in one or more of the moons, as the resonance prevents the orbits from becoming circular. The Io-Europa-Ganymede resonance is the most famous example, but similar resonances exist among Saturn's moons and in other systems. Understanding these resonances is key to understanding the evolution and behavior of moon systems. Some moons have been found to have unexpectedly thick ice shells. Early estimates of the thickness of Europa's ice shell, for example, suggested it might be only a few kilometers thick. However, more recent data and models suggest it could be tens of kilometers thick, which has implications for the difficulty of reaching the ocean below and for the dynamics of the ice shell itself. Similarly, Enceladus's ice shell is thought to be about 20 to 25 kilometers thick globally, although it may be much thinner near the South Pole, where the geysers are located. These thickness estimates are constantly being refined as new data becomes available. Moons can have surfaces that are covered in strange, unexplained features. Despite decades of study, some features on moons remain mysterious. Europa's chaos regions, for instance, are areas where the ice appears to have broken apart and refrozen in a jumbled mess. But the exact process that created them is still debated. Similarly, the strange polygonal terrain on Miranda and the cantaloupe terrain on Triton are not fully understood. These enigmatic features remind us that there is still much to learn about these distant worlds, and that each new discovery often raises as many questions as it answers. Some moons have been studied using radar from Earth. Ground-based radar can penetrate clouds and thin atmospheres, allowing astronomers to map the surfaces of moons like Titan even before spacecraft arrived. By bouncing radio waves off the moon and analyzing the echoes, scientists can learn about the surface's roughness, composition, and topography. This technique has been used to study several moons and has provided valuable data that complements spacecraft observations. Radar studies have revealed, for example, that Titan has large, smooth regions that are likely lakes or seas of liquid hydrocarbons. Moons can have surfaces that are shaped by wind erosion. On Titan, where the thick atmosphere supports winds, the surface is shaped by aeolian processes similar to those on Earth and Mars. Sand dunes made of hydrocarbon particles stretch across Titan's equatorial regions, shaped by prevailing winds. These dunes are among the largest in the solar system, comparable in size to those found in Earth's deserts. The presence of wind erosion on Titan shows that even a cold, distant moon can have active surface processes driven by atmospheric circulation. Some moons have been the target of lander missions. In 2005, the European Space Agency's Huygens probe successfully landed on Titan's surface, becoming the first and so far only spacecraft to land on a moon in the outer solar system. The probe sent back images and data for several hours, revealing a landscape of rounded pebbles and dark, organic-rich terrain. Future missions may land on other moons, such as Europa or Enceladus, to study their surfaces in detail and search for signs of life. Landing on an icy moon presents unique challenges, including the risk of sinking into soft ice or encountering unexpected hazards. But the potential scientific rewards are immense. Moons remind us of the incredible diversity of the solar system. From the volcanic fury of Io to the frozen calm of Callisto, from the methane seas of Titan to the water plumes of Enceladus, each moon is unique. They challenge our assumptions about what a world can be and where life might exist. They show us that water, warmth, and complexity can be found in the most unexpected places, hidden beneath ice shells or locked in tidal embraces with giant planets. As we continue to explore these moons, we learn not just about them, but about the processes that shape all worlds, including our own. Moons teach us about the delicate balance between destruction and creation. They are born from violence, from collisions and gravitational captures, yet they persist for billions of years, quietly orbiting their planets. They are shaped by impacts that scar their surfaces, yet those same impacts can deliver water and organic molecules. They are torn by tidal forces that threaten to break them apart, yet those forces also generate the heat that powers their geological activity. In this tension between opposing forces, moons find their stability, their character, and their stories. The study of moons reveals the interconnectedness of celestial bodies. A moon's existence and evolution are intimately tied to its planet, to neighboring moons, and to the history of the solar system as a whole. The gravitational dance between Jupiter and its moons creates the tidal heating that makes Io volcanic and Europa oceanic. The interactions between Saturn and Titan shape the moon's atmosphere and climate. The capture of Triton by Neptune's gravity may have disrupted the planet's earlier moon system. Every moon is part of a larger system, and understanding one requires understanding them all. Moons offer us glimpses into environments that do not exist on Earth. On Titan, liquid methane flows across a landscape of water ice as hard as rock. On Europa, an ocean lies beneath an ice shell, isolated from sunlight, but potentially teeming with energy from hydrothermal vents. On Io, volcanoes erupt with such intensity that they reshape the surface within months. These alien environments challenge us to expand our understanding of what is possible, to consider forms of chemistry and geology that have no parallel on our home world. They remind us that the universe is far more creative than we can imagine. The search for life on moons is one of the most exciting frontiers in science. If life exists beyond Earth, it may well be found in the hidden oceans of Europa or Enceladus, in the methane lakes of Titan, or in some other unexpected location. The discovery of even simple microbial life on another moon would transform our understanding of biology and our place in the universe. It would tell us that life is not unique to Earth, that it can arise wherever the right conditions exist, and that the cosmos may be teeming with living things, each adapted to their own unique environment. The quest to find this life drives much of our exploration of moons, and will continue to do so for decades to come. Moons are windows into the past and keys to the future. Their ancient surfaces preserve the record of the solar system's violent youth, a time when impacts were common and planets were still taking shape. By studying moons, we learn about the conditions that existed billions of years ago, and the processes that led to the formation of the solar system we see today. At the same time, moons may hold the resources we need for future exploration: water for drinking and fuel, minerals for construction, and organic materials for sustaining life. They are stepping stones that could one day help humanity expand beyond Earth and into the wider solar system. In the end, moons are companions. They orbit their planets faithfully, shaping tides, stabilizing rotations, and adding beauty to the night sky. Earth's moon has been our constant companion for billions of years, a witness to the rise of life and the evolution of our planet. The moons of other planets serve the same role: silent guardians that orbit in the dark, reflecting sunlight and holding secrets beneath their surfaces. They are not lifeless rocks, but worlds in their own right, each with its own history, its own geology, and perhaps its own potential for life. And now, as the stars begin to dim behind your thoughts, we have wandered together through 100 quiet truths. From the largest moons to the smallest, from ancient cratered surfaces to young, active landscapes, from icy shells to hidden oceans and everything in between. You have traveled across volcanic plains, beneath frozen seas, and through plumes of water that reach into space. You have glimpsed the pale light of distant suns reflected off surfaces of ice and methane, and you have marveled at the delicate balance that allows these worlds to exist. You are part of a universe that creates moons as companions to planets, worlds within worlds that orbit in silence through the dark. The atoms in your body once belonged to stars, the same stars that forged the iron in Ganymede's core and the sulfur on Io's surface. You are connected to these distant places in ways both ancient and profound. Tonight, as you rest, the moons continue their silent dances. Ice shifts on Europa, geysers erupt on Enceladus, methane rain falls on Titan, volcanoes glow on Io, And far away, in the depths of space, other moons orbit other planets around other stars, each one a world of its own, waiting to be discovered. You have done enough for today. There is nothing more you need to do. Close your eyes, let your breathing deepen. Let your body relax into the quiet darkness. Feel the gentle pull of sleep, as inevitable and natural as the moon's pull on the tides. Rest now. Dream of distant shores beneath alien skies. Dream of oceans beneath ice and geysers reaching toward the stars. Dream of worlds that orbit and turn in the endless cosmic night. Good night.